Welcome to chapter 9. So in this chapter, let's talk about models of chemical bonding. So in this lecture, we'll talk about atomic properties and chemical bonds. We'll talk about the ionic bonding model, the covalent bonding model, no bond energy and chemical change, between the extremes where we talk about electronegativity and bond polarity, and we'll talk about an introduction to metallic bonding. So let's talk about the comparison between metals and non-metals in the periodic table. If you notice that in this diagram, everything that you see in blue is metals, everything in yellow is non-metals, and the ones that are in between metals and non-metals are metalloids. So those metalloids are boron, silicon, germanium, arsenic, lead, and tellurium. So these are some of the materials that are generally called metalloids, and I have the properties that are given here in terms of their chemical periodicity. And make sure that you revise the last chapter so that it becomes easier to understand this chapter. Now, let's talk about chemical bonding. So what are the types? So there are three types of chemical bonding. First is ionic bondings, covalent bonding, and metallic bonding. Ionic bonding involves the transfer of electrons, and it's generally observed when you have a metal bonding with a non-metal. You have covalent bonding, which involves sharing of electrons, and it generally is observed when you have a non-metal bonding with another non-metal. And you have metallic bonding that involves electron pooling, which occurs when a metal bonds with a metal. So when a metal bonds with a non-metal, it creates ionic bonds. When a metal bonds with non-metal bonds with a non-metal, it creates covalent bonds. And when a metal bonds with a metal, it creates metallic bonding. Now, so there are three models that we talked about. First one is the model that we talked about where a metal reacts with a non-metal, which forms ionic bonding. Here, the metal donates its electrons to the non-metal, causing electron transfer, and the donated metal ion becomes positively charged, a cation, and the non-metal becomes negatively charged, which becomes the anion. So thereby resulting in the formation of an ionic solid because of the interactions between the positively charged, because of the cation and anion. So the next type of bonding is a non-metal bonding. So where we talk about non-metal and non-metal. So the non-metals they do not donate electrons, but rather share electrons among them, resulting in the formation of a covalent bond. In an ionic bond, the structure is generally crystalline, meaning that the ions themselves bond together to create a crystal-like structure. But in covalent molecules, the molecule itself, in covalent bonding, the molecule itself forms an entity, and that entity itself acts as the single part. Here, in ionic solids, most of the forces are intramolecular forces, but in covalent solids, the covalent bonding, the forces that act upon the materials are generally intermolecular forces. We'll talk more about intermolecular forces as we go into inorganic too. Next, we talk about metallic bonding. Metallic bonding involves metals that come together and create an electron pool, because notice that metals themselves are ready to give away electrons. They have high electroaffinity, so that they have really low electron affinity, so which means that they are ready to donate their electrons, creating this electron pool. And the electron pool resembles that of water, and the ions themselves stay as the core, but the electrons themselves form a nice pooling around the ions. So there is a gradation between the type of bonding that happens in the periodic table. You go from good ionic bonding towards really covalent bonding, and then you go towards metallic bonding. So there is a lot of phase differences between the type of bonding that occurs. Some bonds can be a little bit metallic as well as ionic. Some bonds can be metallic and covalent at the same time. Some bonds can be ionic and covalent at the same time. So these are molecules that undergo what we call gradation. Gradation is where there is a slight interference between the type of bonding that happens there. So the best method to represent bonding is the Lewis electron dot symbol method. So how do you draw the Lewis dot symbols here for any main group element? First, we have to note the A group number which gives the number of valence electrons on each of those particular atoms. Now place one of the dots at a time on each of the four sides of the element symbol and keep adding dots and pairing them until all are used up. So make sure that you have, for example, nitrogen here can be written in all these forms. So notice that we are writing the pair as a single entity and all the single electrons as separate entities. But notice, because the reason we do that is because we want to make sure that we can pair this to different atoms. So for a metal, the total number of dots in the Lewis symbol is the number of electrons that the atom loses to form a cation. But for a non-metal, the number of unpaired dots equals the number of atoms that it gains to form an anion, or the number it shares to form a covalent bond. Remember that a non-metal can create both an ionic bond as well as a covalent bond. So that's the reason why it can do both the things. Either it gains electrons that it lacks to create an ionic bond, or it shares its electrons with another atom to form a covalent bond. So the octet rule here states that whenever the atoms bond, they lose, gain or share electrons to attain the fill outer level of 8. So once they reach a fill outer level of 8 electrons, that's when we call that this is a stable structure. So stability comes from the octet here. That octet rule is generally 8, but for it is 2 for hydrogen and lithium. So these are electron dot symbols for different elements in period 2 and period 3 of the main group elements. Notice that the group number itself shows you the number of dots on the atom. So if it is 3, so you have 3 dots. If it is 4, you have 4 dots. So this way we can see that the group number itself denotes the number of valence electrons on that atom. So let's start with the first one, the ionic bonding model. So how does an ionic bond form? So it forms when the metal transfers electrons to a non-metal to form ions, and which these ions attract each other in turn to create the solid compound. Now here the total number of electrons that is lost by the metal atoms equals the total number of electrons gained by the non-metal atoms. So this is important because the number of electrons itself can balance the equation. So let's take an example of the formation of lithium fluoride. There are 3 ways we can depict this. The first way is by electron configuration. So we have lithium, which is 1s2 2s1. We have fluorine, which is 1s2 2s2 2p5, which forms lithium plus. Notice that this 2s electron is donated to the fluorine, creating Li plus, which becomes 1s2, and F minus, which becomes 1s2 2s2 2p6. Notice that this 1 electron is the one that goes to the fluorine atom. So once this electron gets transferred, so this is the first method. The second method is using the orbital diagrams. In the orbital diagrams, we move the electron from the first element to the second element to create the structure. So what are we doing here? The electron that was here will be sent to the last orbital on the fluorine atom, resulting in the formation of LiF bonding. The last method is the Lewis electron dot symbol, here where we move the dot from lithium onto the fluorine and create Li plus, and F, which has excess electrons, becomes negatively charged. So these are the 3 methods that we use to represent the structure. So here they are asking us to use partial orbital diagrams and Lewis symbol to depict the formation of Na plus and O2 minus ions to form the atoms, determine the formula of the compound that it is forming. So let's start with Na plus. So sodium and oxygen. Sodium has a Z of 11, oxygen has a Z of 8. So if you write its electronic configurations, so sodium, if you want to write it, the easiest method is to draw the Lewis dot symbol. So sodium is a 1a group element, so there is 1 electron on sodium, and oxygen is a 6a group element, so there are 6 electrons and two electrons that are unpaired. So notice that there are 2 electrons that are paired. So these are the ones in red here are the ones that are already paired. So the ones in black are the ones that are unpaired. So what is going to happen? So for it to form a bond here, it needs to become octet. So the oxygen requires 2 different electrons, which means that there should be 2 different sodium atoms. So there should be 2 different sodium atoms. So these electrons have to be donated to the oxygen. In this process, it creates Na plus, and oxygen here gains the electrons that it has and becomes negatively charged. And you have 2 sodium atoms that are created here. So you have Na plus and Na plus. So the compound that you end up with is Na2O. So Na2O is the structure that ends up forming. So you have sodium oxide. So remember the naming of ionic compounds. You start with the cation. The cation is sodium and the oxygen is the anion. So the sodium here, and oxygen is the one that becomes ide. So it becomes oxide. So sodium oxide. So this is the name of the compound that is created in this process. Now, most of these ionic reactions are generally exothermic. So for example, sodium bromide, you have a sodium which is a really inactive metal, and you have bromine which is a non-metal. So the both combine to have an exothermic reaction resulting in the formation of sodium bromide. Now, to represent what happens inside an ionic reaction, we have to remember what is actually happening in each of the processes that are creating the final solid. So to explain that, we use the Born-Haber cycle to explain the formation of an ionic compound. So the first thing that happens here is that the lithium here exists as a solid, and you have fluorine that exists as a gas. So the first thing that has to happen is to create lithium gas. So lithium, which is a solid, for us to be converted into gaseous particles, which requires addition of energy, and then it starts bonding with fluorine. Now once lithium becomes gaseous, it has a lot of energy, so it starts attacking the fluorine atoms and splits the fluorine atoms into creating fluoride ions. So monofluoride ions. So that requires a little bit of more energy, and once the lithium and fluorine form the individual monoatoms, now they start reacting with each other, where lithium starts donating its electrons to fluorine, creating Li+, and the Li+, the electrons are freely moving around. Now the fluorine will catch those electrons, resulting in the formation of F-. Finally, both Li+ and F- start coming down and forming a lattice structure. So lattice structure here is a solid crystalline structure. So it creates the solid crystalline structure, which results in the formation of the final bond. So this is the idea behind the formation of lithium fluoride. Now let's talk about lattice energy. So lattice energy is the energy required to separate 1 mole of an ionic solid into gaseous ions. So remember that this energy here itself is the negative of the lattice energy. So lattice energy is the energy required to split an ionic solid to create its gaseous ions, is basically called as lattice energy. So it's a measure of strength of the ionic bond. So one way we can measure the strength is by Coulomb's law. So Coulomb's law states that the electrostatic energy is proportional to the product of the charges and inversely proportional to the distance between them. So in terms of the actual ionic bond itself, so it's proportional to the cation charge and the anion charge, and it's inversely proportional to the distance between the two charges. So when you have large atoms, that means that there is less electrostatic, and when there is large atoms, there is less electrostatic energy. The smaller the atoms, the larger the electrostatic energy. In terms of the ions, the higher the charge, the higher the energy. Now let's talk about the periodic trends in lattice energy. So lattice energy is affected by two things. One, its ionic charge. The second is ionic size. Now as the ionic size increases, automatically lattice energy decreases. The reason mainly is because the cation anion radius will start increasing rapidly, which results in the decrease of lattice energy. Now, so lattice energy therefore decreases down a group in the periodic table. Now as the ionic charge increases, the lattice energy increases. This is obvious because as the higher the charge, the higher the electrostatic energy between the two atoms. So among the atoms that create the first, if you take group 1A atoms, lithium fluoride is the element that has the highest amount of lattice energy, followed by the second, the sodium atoms, the atoms that are formed by sodium, and then you have potassium atoms, then you have the final rubidium atoms. So try to solve this problem. First, they're asking you use the ionic properties to choose the compound in each pair with the larger lattice energy. They're asking you rubidium iodide and sodium bromide, KCl and calcium sulfate. So pause the video of what you have just learned right now and try to apply this to this problem and try to solve for the answer. Next, let's talk about the properties of ionic compounds. So ionic compounds tend to be really hard, rigid and brittle, and they generally have high melting points. And these ionic compounds do not conduct electricity in the solid state. So in the solid state, the ions are fixed in place in the lattice and they do not move. and these ionic compounds conduct electricity when melted or dissolved. So in the liquid state or in solutions, the ions are free to move and they generally carry a current. So why do ionic compounds crack rather than bend? The reason mainly is because when you hit a crystal, you're displacing the charges, which results in the like charge repulsion, which can end up cracking the crystal because the like charges will try to repel each other, and as they repel each other, they are trying to push one away from the other, which results in the breaking of the ionic compound. This is the reason why ionic compounds are generally brittle. So this is also one other property that can enhance the idea of ionic compounds is electrical conductance. So a solid ionic compound is an insulator, but a molten ionic compound can conduct a little amount of electricity, but once you dissolve an ionic compound in water, the water starts breaking the ionic compound into its individual ions, resulting in easy flow of charge from one point to the other point. So this is a table that shows different melting points and boiling points of some ionic compounds. Note that the larger the ionic compound, the larger the lattice energy, the larger the melting and boiling points. Right. So with that we end the topic on ionic bonds. So next let's talk about covalent bonds. So how do covalent bonds form? Here let's talk about the formation of a covalent bond of hydrogen. So the idea inside a covalent bond is that you have two atoms, two nonmetals that come closer and closer to each other. As they come closer and closer, you notice that there is an amount of repulsion that happens between the positive charges, and there is also attraction between the negative charges, between the negative and the positive charges. This leads to a situation where at a certain point, it comes to a point where the atom undergoes what we call equilibrium, where the repulsion of like charges becomes equal to the attraction of the unlike charges. This attraction, when it becomes equal to the repulsion, this is the point where you call it the conversation, you call it the bond formation, where it forms the covalent bond. So that distance is called as the covalent bond length. So let's talk about two types of lone pairs. So when we have bonding pairs and lone pairs. So atoms generally share electrons to achieve a full outer level of electrons. So this shared electrons are generally called as the shared pair or the bonding pair. But not all of them are the shared pairs. Notice that when you have a shared pair, we represent it either by two dots or a bond, a single line. So an outer level electron pair that is not involved in the bonding is called as the lone pair. So for example here, these are examples of lone pairs. So these are all lone pairs. Because notice that these are the electrons that are not involved in the sharing process. Only the electrons that are involved in the sharing process are called as the bonding pairs. Electrons that are not involved in the bonding process are called the lone pairs. So next let's talk about the properties of a covalent bond. So covalent bond depends on what we call the bond order. So bond order here represents the number of electron pairs being shared by given pair of atoms. So for example, if you have a single bond, it means there is a one bonding pair and the bond order is 1. If there are two different pairs that are being shared, we call it a double bond. Then there are two bonding pairs and the bond order is 2. In the same way, if there are three lone pairs that are being shared, if there are three bonding pairs, which means that we call it a triple bond and the bond order is 3. Next term is the bond energy. Bond energy is the energy needed to overcome the attraction between the strong nuclei and the shared electrons. So this is the energy that is required to basically break the bond. So the stronger the bond, the higher the bond energy. Next is the bond length. So bond length here is the distance between the nuclei of the bonded atoms. So remember that bond length is the actual distance between the two nuclei. This distance is called as the bond length. Next, let's talk about trends in bond energy, bond order, energy and length. So for a given pair of atoms, a higher bond order results in a shorter bond length and a higher bond energy. So remember this, higher the bond order, that results in a shorter bond length. The shorter the bond length, the higher the bond energy. So for a given pair of atoms, a shorter bond is always a stronger bond. So when you go down a group, the bond length will increase because the atomic size increases, and it decreases across the period because the atomic size decreases. Now bond energy actually shows the opposite trend, because remember that the shorter the bond, the higher the energy. So as you go down a group, the bond energy will decrease. As you go across the period, the bond energy will increase. So this is a table that shows different bond energies of different bonds. For example, if you take carbon and hydrogen, the bond energy is around 413 with a bond length of 109. So this is a table that shows you the general bonds. You can also see there are bonds that are multiple. For example, multiple bonds end up giving more energy than needed. So the higher the bond order, the higher the energy and smaller the length. Now let's talk about bond length and the covalent radius. So we have an internuclear distance. Internuclear distance is the bond length, and the covalent radius is generally half of the original value of the bond length, and we round it off to the nearest value. That rounding off value is what we generally call as the covalent radius. Now the higher the bond order, notice that there is a decrease in the bond length and there is a higher increase in the bond energy. So the higher the bond order, the lower the bond length and the higher the energy. Now, so they're asking us to use the periodic table and rank the bonds in the set of decreasing bond length and decreasing bond strength. So you have sulfur fluorine, sulfur bromine and sulfur chlorine. Notice that you're going down across the period, you're going down across the group. As you go down across the group, we know that the bond length actually decreases, so which means that SCl is generally, so they are talking about the decreasing bond length, so which means that SCl is the largest one. The next one is SBr is the largest one. So SCl is the shortest one and SF is the smallest one. So this is the decreasing order in terms of the bond length. Now decreasing bond strength, the smaller the one, the larger the energy. So this is bond length. In terms of bond strength, so SF has the highest one, next SCl, next SBr. Here this is the bond energy in terms of the decreasing order. Now in terms of the energy in the bond here, notice that you have C bond O, C double bond O and C triple bond O. So notice that the bond, the higher the bond order, the shorter the wavelength. So in terms of the decreasing value, the largest one is C double bond O. Next one is C bond O. You have next one is C double bond O. Next one is C triple bond O. So in terms of decreasing bond length. In terms of the decreasing bond strength, it's reversed. So this is the decreasing bond strength. So this will be the highest and this will be the lowest. So this is the idea here of how to solve this problem. Next, let's talk about the strong forces within molecules and the weak forces between them. So the strong forces are the forces between the inside the molecule itself. We call them the strong forces, and the weak forces are the forces between the two molecules. So strong forces in general are generally within the molecules and they cannot break by physical change, but weak forces can be overcome by physical change. So to change the bond, to change the actual strong force, we will have to use chemical change, but weak forces can be changed by physical change. So this is a difference between, this is a covalent structure of network covalent solids. So network covalent solids are solids that can have a network structure which results in the formation of a stronger material. So the two examples that we see here are, say, quartz and diamond. So quartz generally has a layered structure, that's why it's generally much less stronger. But diamond here has a three-dimensional hexagonal structure. Because of the three-dimensional hexagonal structure, it's much more stronger. Next, let's talk about bond energies and enthalpy of reaction. So the heat released or absorbed during a chemical change is generally due to the differences between the bond energies of the reactants and the products. So the enthalpy of reaction can be written as the energy of the reactant bonds that are broken plus the energy of the product bonds that are formed. So let's take an example here. So you have the formation of HF here, which involves 2 hydrogens and 2 fluorine atoms. Now each bond requires 432 for hydrogen and 159 for fluorine. So once we break those bonds, notice that they become atoms. So that's the energy that we've added. Now we have to form the bonds. So the bond formation here results in HF, and each of these bonds requires 565 kilojoules. Now the energy required to bond the products is negative 1130. The net value of plus and minus is the delta H value. So we always remember this value, that whenever we break bonds, we consider that to be positive. Whenever we form bonds, we consider that to be negative in terms of the energy. So pause the video here and try to solve this problem here. So from the table we have, so these are the values we have. So you have 4 bonds of CH and 3 chlorine-chlorine bonds. So that means we have to take in consideration 4 CH bonds and 3 chlorine bonds. So 4 CH bonds is 413 and chlorine bonds is 243, which is a total of 2381 kilojoules. And for the second part, to form the bonds, so you have 3 Cl bonds, which result in the formation of about negative 339 kilojoule. And you have 1 CH bond, so that value is about negative 413. And you have 3 HCl bonds, which is about negative 427. So when you end up adding all of it, you get negative 2711 kilojoules. So when you add both those values, you end up with negative 330 kilojoules. Notice it that this is an exothermic reaction. So these are some examples of enthalpies of reaction for combustion, where you add oxygen to this and burn it in presence of oxygen. So vegetable oil gives you around negative 37 kilojoules per gram. Butter gives you around negative 30. But the same values when you go towards carbohydrates are much lower in comparison. The reason mainly is because fats generally do have a lot more bonds, and that means that there is a lot more energy that can be released. Next, let's talk about electronegativity and bond polarity. Now, a covalent bond in general is where there is a shared electron pair, but if the shared electron pair is not shared equally, which means that one atom is trying to pull the electrons towards itself, we call that type of a bond a polar covalent bond. So this type of a bond is what results in the formation of what we call polar molecules. So polar molecules are molecules where there is no equal distribution of charge throughout the molecule, and one of the atoms tries to pull the electrons towards itself, resulting in a distorted view of the molecule by itself. So the ability of an atom in a covalent bond to attract the shared electron pair this property is called as electronegativity. And this electronegativity is the reason why there is unequal sharing of electrons, which causes more electronegative atom to be partially negative. So the electronegative atom will become partially negative because it attracts the electrons towards itself, and the atom that is having less electronegativity will become partially positive because it's being deprived of the electron pair that is meant to be shared equally. Now let's take the 3 phases of how polar covalent bonds and where does it lie. So on one end of the spectrum we have pure ionic bonds, where there is a complete share of electrons that are being transferred from the metal to the non-metal, resulting in the formation of 2 charges, a positive and a negative charge, which creates the pure ionic bonds. On the other end we have pure covalent bonds, where 2 identical molecules will share the electrons equally among themselves, resulting in the formation of a pure covalent bond. And in between both of them you end up getting polar covalent bonds. Polar covalent bonds are molecules where there are 2 different molecules with different electronegativities. Due to the different electronegativities, it ends up having the more electronegative atom will try to pull the electrons towards itself, and the less electronegative atom will become partially positive, and the more electronegative atom becomes partially negative. So these polar covalent bonds are generally much more common than either pure ionic or pure covalent bonds because of the state in which bonding generally occurs. So this is a scale of Pauling's electronegativity scale. This is the common scale that is used to represent the electronegativity of different atoms. Notice that the electronegativity increases across a group, across a period, and decreases down a group. So in a group, it decreases, and in a period, it increases. So remember these two properties. So let's talk about the trends in electronegativity. The most electronegative element is fluorine. Now, electronegativity decreases down a group because the atomic size will increase. In the same way, electronegativity increases across the period because the atomic size decreases. So non-metals in general tend to be more electronegative than metals. So this is one of the most primary important properties to remember. So that metals generally have less electronegativity because they're ready to donate electrons. The non-metals are generally ready to accept electrons. That's the reason why they have higher electronegativity than metals. So this is in terms of the electronegativity. Next, let's try and understand the difference between electronegativity and oxidation number. So you can use electronegativities to assign oxidation numbers. So remember that the more electronegative atom is generally assigned all the shared electrons. The reason mainly is because it can pull the electrons towards itself more often than the less electronegative atom. Now, the less electronegative atom is assigned none of the shared electrons. So each atom in a bond is assigned all of its unshared electrons. So how do you calculate the oxidation number? Oxidation number is the number of valence electrons minus of the number of shared electrons plus unshared electrons. So for example, let's take an example of HCl here. So here we know that chlorine is more electronegative than hydrogen. So for chlorine, we can write that the valence electrons is 7 and it plucks the 2 electrons towards itself. So it shares 2 electrons here and the unshared electrons are the 6 electrons here. So the oxidation number becomes -1. Now when you take hydrogen, notice that here we wrote both the shared electrons towards the chlorine itself. The reason we write this way is because of the fact that it is a more electronegative atom. Now hydrogen here is less electronegative than chlorine, so for it we can write valence electron is 1. The shared electrons is 0 because we are assigning all of it to chlorine, and the unshared electrons, there is no unshared electron, so oxidation number becomes +1. So hydrogen gets a +1 oxidation number and chlorine gets a -1 oxidation. So how do you depict these polar bonds? So the unequal sharing of electrons can be depicted by using a polar arrow. So this polar arrow is where we write a plus on one side and extend the arrow and point the arrow towards the more electronegative atom. So remember that the head of the arrow points towards the more electronegative element. So a polar bond can also be represented by using del plus and del minus. Del here represents partial charge. So when you write del plus, it means partial positive charge, and del minus means partial negative charge. Now, what kind of electrode, how do you judge whether a bond is electronegative or not, polar covalent or ionic? Now, in general, we take into consideration the difference of electronegativity as a good measure of checking what type of bond a given particular structure is. Now, if the electronegativity is less than 0.4, it lies between 0.0 and 0.4, we consider that mostly covalent. Now, if this electronegativity lies between 0.4, if this difference in electronegativity lies between 0.4 and 1.7, we consider this to be polar covalent. And if this electronegativity difference between the two atoms is greater than 1.7, it generally is mostly ionic. So these are the three main conditions that we use to judge a given type of bond. So the difference in electronegativity. So difference in electronegativity is the electronegativity difference between the two atoms. So for example, if it is ENA minus ENB. So this is the value that we are choosing to represent the type of bond that is being formed. Now, so they're asking you to use a polar arrow to indicate the polarity of each of these bonds. You have NH, you have FN, and you have ICl. So for nitrogen, we know that the electronegativity is 3.0 and hydrogen is 2.1. So whichever is more electronegative, the arrowhead will point towards that. So this is the bond direction. For nitrogen and fluorine, we know that fluorine is the one that has higher electronegativity. So it starts at nitrogen, it goes towards fluorine. Now for ICl, I is 2.5 and chlorine is 3.0. So we start at I and we go towards chlorine. So this is how we can write down the arrows. So they're also asking you to write it in terms of increasing polarity. You have hydrogen, nitrogen, hydrogen, oxygen, and hydrogen CH. So the highest polarity comes with the atom that's on the extreme end of the cycle. On the extreme end of the cycle, we have hydrogen and oxygen. So which means this is the one that becomes the most polar structure. So the least polar structure is hydrogen carbon. Next we have hydrogen nitrogen. Next we have hydrogen oxygen. So this is the way in which we can write the cycle here. Now, let's talk about the last type of bonding, which is metallic bonding. So the electron C model of metallic bonding proposes that we have all metal atoms in the sample contribute to their valence electrons to form a delocalized electron C. Now, the metal ions here in general have a nuclei with the core electrons will lie in an orderly array within this mobile C. So remember that these are the ones that are corely inside the structure, and all of the atoms in the sample will share the electrons. So this is what we call as a free electron theory of metallic bonds. So free electron theory basically states that all of the metal core ions will stay inside while the electrons float and move around. This is one of the ways we explain the conductance of metals. And these metals are generally held together by the attraction between the metal cations and the sea of valence electrons. And this is why the metals stay intact. So next let's talk about the properties of metals. So metals in general are solids. They generally have moderate to high melting points, and they generally have very high boiling points. And these melting points can decrease down a group and increase across the period. Again, this results, the reason mainly is because of the presence of the atomic size. So as you go down the period, the atoms become larger. The larger the atoms, the easier it is to melt the structure. The smaller it is, the harder it is to overcome the energy of these bonds. Now the metals can also be shaped without breaking. So this property is called as ductility. So this is one of the main properties by which human civilization has moved forward, because without this property it would have been hard to make any in general structures. Now the electron C here is the one that allows the metal ions to slide past one another. So we'll talk about it in the next slide. Now metals are also good conductors of electricity in both solid and liquid states. So again, here also the electron C is mobile in both phases, and these metals are really good conductors of heat. Again, there also the electrons C plays the important role. So these are some melting points and boiling points of metals. For example, if you look at a larger metal like uranium has a melting point of 1130 and a boiling point of 3930. So the larger the metal atom, so you notice the difference in melting points and boiling points. And for group 1A in general, they have really low melting points, but once you start going towards group 2A, you notice the ironic, the amount of change that's going to happen due to the metals here. Now, why do metals not bend rather than crack? The main reason is because remember that we talked about in ionic bonds why it cracks. The reason they crack is because it ends up creating this difference in the arrangement of the ions. The ion arrangement, once it becomes altered, it can also push the electrons away. So like charges will repel each other. This results in the cracking. But metals have an electron C. The C itself will deform. So when the metal deforms, the electron C undergoes a deformation. This results in the actual metal bending rather than the metal breaking into parts. So what will happen here is the electron sieve will arrange itself in such a way that it doesn't let the metal crack, and once it reaches a certain point it can also break. That point in general is called as the breaking point or the fracture point. So we will talk about it more in physics, but that is to the end of what the topic about metals is. So with this we end the topic on the models of chemical bonding. I will see you again in the next lecture.